So I'm Bryant. I used to work at Twitter on this stuff. I now work on Stripe. I work at Stripe and still try to use as much of this tech as I can because I'm used to it. And so this is a talk about an application of scalding and especially of Algebird. We use it at Stripe for machine learning, and in particular for training decision trees. And so the title of this talk is Adding Tree and Tree, but a more descriptive title is probably this. So Brushfire is a distributed generic framework for distributed generic decision tree learning using scalding and Algebird. And it's open source. You can find it on GitHub. And so you know, Hadoop talks are classically about counting. You know, and the word count example is sort of always used, but as you've heard from Oscar and Ian, we like to think about adding, really. And so this is sort of a talk about counting, but it's really a talk about adding, and in particular, it's a talk about adding trees. Let's talk about adding decision trees. So what's a decision tree? So a decision tree is a particular kind of machine learning model where what you're trying to do is make some prediction, right? So the basic interface for this and for a lot of different kinds of models is you have this predict method, right? And you feed it some set of attributes. Some call it just map from strings that maybe are names of attributes, names of features like size or color or whatever. And the associated values, and you get back something, right? So to make this a little bit more concrete, you might have a predictive model as to whether or not a particular Muppet likes cookies, okay? And so the features that go into this prediction might be their height, might be their color, might be what they wear, and the output of the model is an answer to the question of do you like cookies? And so a very simple tree model that might answer this, a sort of as simple as possible tree model that might answer this might look like this. And I'm going to talk a little bit about how these models work when you evaluate them, but just to sort of be clear, this talk is principally about how you build these models, right? So evaluating them is then kind of the next step. So you know, does Cookie Monster like cookies, right? And so the way you evaluate this is you start at the root, and the root node sort of represents, you know, the entire space of possibilities here. And then you ask a question. You have some predicate. You know, is the color associated with this instance blue? And based on the answer to that for this particular instance, this particular observation that you're feeding into this, you go either to one child or the other, right? So OK, in Cookie Monster's case, it is blue, and so you go to that node. And then you have some prediction that's associated with that node, and that is the result that you return. So yes, Cookie Monster does like cookies, so that's good. But you know, you might have a prediction, you might have a leaf node, or you might keep going, right? So these are trees, they're recursive structures, and so you might go down the other path, color's not blue, and then you would get to another interior node where you would have another predicate, right? So does you wear stripes? And so we're going to say here, you know, that Bert does like cookies and you know, that Oscar doesn't. No relation to the Oscar who spoke earlier, I guess. And so that's what the tree looks like. And so I said, you know, when I showed this interface here, I showed it returning a prediction as type T. Right? And so what you want to think about conceptually with this tree is that you've got these T values sitting in the nodes that are the predictions. And you know, the job of building this tree is really twofold. One is to kind of come up with the structure of the tree, what the predicates are, in what order, and so on. And then the other is coming up with those predictions in the nodes, right? So what type is that? So you might think about different models, different kinds of models, having different types in those leaves. So you might have what people call in machine learning a binary classifier, right? Which is, do you like cookies, yes or no? Okay? And the type in that case that you really want to get back is a Boolean. You might have a regression where the type you get back is the answer you get back is some kind of numeric value, right? How many cookies will you eat? So then you might have an int or a double or something like that in the leaves. You might also have a multi-class classifier, not a binary classifier, right, where there's a series of discrete values, like what's your favorite kind of cookie? And so the values in the leaves are going to be some kind of string, right? These are all different kinds of things, but the structure is the same. And so when I talk about Brushfire being a generic framework for distributed decision trees, right? That's one aspect or part of what I mean by it being generic, right? It tries as much as possible not to make concrete decisions about this. This is going to be a Boolean. This is going to be a string, whatever, but to use generic type parameters like this is just some prediction type T, right? And so most machine learning frameworks, there's this huge space of possibilities, even just if you're constrained to talking about decision trees of, what function are you going to use to evaluate it? Is this a classification or a regression? How are you validating it? Are you doing it with some kind of out-of-time validation or some kind of out-of-bag validation or k-fold cross-validation or whatever? If you have trees, how do they split? Do they have binary splits or multi-way splits? Do you have multiple trees in an ensemble and so on and so on and so on, right? And so Brushfire, Oscar said this great thing about how, we just like to write these beautiful abstract traits and like leave other people to implement them, right? Brushfire is sort of applying the same philosophy to machine learning, right? I don't care. Someone else can go implement all of those, right? I just want to set up what the traits are. What are the kind of abstractions that make up a decision tree learner, right? And so let's keep talking about this prediction type T. So I said that for binary classification, you might think of it as having Booleans in the leaves as the predictions. That's actually a very naive binary classification, right? Usually you don't want a hard yes/no answer. Usually you want maybe some kind of probability out, right? You want to know, what are the chances this is true? What are the chances this is false? And so you might think that maybe, OK, the right thing for a binary classifier is to have a double with probability. The problem is, or let's say an additional constraint on this framework is that we want to be able to compute this in a distributed way. And if you think about where those predictions are coming from, where they're coming from is some input set of training data, right? We have a bunch of examples. And we're going to look at what leaves those examples fall in. And we're going to want to look at what the target values, the do you like cookies or whatever, are for all of the examples we have for some leaf. And so what do we want to be able to do? We want to be able to add up all of those examples that are at a leaf, right? And we want to be able to do this efficiently, which means that we want the values that are in our leaves to be something that we can compute in this kind of distributed, aggregation way that Oscar and Ian were talking about. So from a type class point of view, whatever our value T is there, we want it to be a monoid, right? We want it to be something that we can sum up. And so the problem with using just a double in that case is that it doesn't sum the way we want it to, right? If we have a whole bunch of instances and they've all got like ones and zeros for whether or not they like cookies, for the individual probabilities of whether or not they like cookies, and you add those all up, you don't get the probability, right? What you need is some kind of average. So you need something better. And so for binary classification, what turns out to be, or one type that is useful, one very simple type that's useful, is just a map that counts the trues and the falses, right? And so really what you get to is that you think of these less as predictions and more as distributions. Really what we want in the leaves actually is a distribution that represents all of the examples that we have for that leaf. And that has a bunch of nice properties. It has the nice properties that you can add them up. It has the nice properties that you can combine them, right? So if I prune away these two leaves, and I want to know what the prediction should be for just this interior leaf, then I can do that very simply, right? I just add the two distributions of the leaves, and now I know what the distribution is for the interior node. You can also think about this, if you want to think about this in kind of a Bayesian way, as I want the predictions to be updatable, right? So we want to have a prior. We want to be able to turn the crank and with new information and come out with a new prediction, right? And so saying it's summable or saying it's updatable really kind of amounts to the same thing, right? And so the other constraint that I put on this framework is that, we talked about it being generic, and I also talked about it being distributed. And so why is it important for this to be distributed, apart from that it's like a fun intellectual problem? And if you already have this constraint that it has to be generic, then it's probably not going to be fast, right? So usually, the usual approach to building this kind of machine learning algorithm is you have some very well optimized code that's using, you know, ultimately fast, like Fortran matrix multiplication or something under the covers, and runs one particular algorithm really, really well. And that's great, you know, if you're running this on some single CPU with a lot of memory, which is kind of typically how you do this, right? But it runs like one algorithm. And if you want this to be generic, which I do, then you're going to be slow, which means you need to be able to throw a lot more computing power at it, which means it needs to be distributed, right? It's also the case that in general, if you have more training data, you're going to get better models out. And in particular, you know, when you say that, people tend to sort of immediately jump to, OK, you have a lot of observations, a lot of examples to look at. And it's true that that's useful. But also, it's really useful to be able to have a huge number of features that you're considering, right? So not just a lot of rows, but a lot of columns. And so that's an important design characteristic for this. And finally, sort of, you know, it's like, why do you rob banks? That's where the money is, right? Why do you want this to run on Hadoop? That's where the data is. And so a lot of people just, you know, a lot of organizations, the interesting data to train machine learning models on is already sitting in an HDFS cluster. And so the kind of convenient, pragmatic thing to do is to have your training algorithms be able to run on an HDFS cluster, right? So at Stripe, you know, we certainly don't have Twitter scale of data. We're dealing with transactional data rather than, you know, clickstream data. We probably could, and sometimes do, you know, get a big enough machine to run these algorithms, you know, on a single node, but it's just so much more convenient to just throw it at the cluster because that's where the data already lives, right? So what does this look like in practice? So here's an example of what it kind of looks like to train a tree in Scalding. So this, you know, some of this should kind of look familiar from earlier talks, but basically, you need some kind of training data which Brushfire expects to be in this instance case class, and we'll talk more about that in a moment. And you need to feed that sort of distributed collection of instance objects into a trainer, and then you can ask the trainer to do things like expand. And what I mean by that is that what the trainer is doing is recursively building up this decision tree, starting at the root, and then recursively adding a layer. And it uses actually 2 MapReduce steps, but only 1 full scan through the data for each new layer of the tree that it needs to add. And so when you say expand repeatedly 10 like that, what you're saying is like add 10 layers of depth to my tree. And that's going to kick off this sequence of like, you know, 20 MapReduce steps, right? And 1 at the beginning to initialize the root. Yeah, so you know, again, recursively, right? You know, you have this tree. It's got these predictions in the leaves, but we want to make it bigger, and so each leaf splits, and then we want to run it again, and each leaf splits, and so on, right? OK. But we have a base case. We need a base case. We need to actually be able to create the root to begin with before we start expanding. And conveniently, that's a simpler thing to start talking about. So how does this actually work? What does this actually do? OK, so you have the training data. You need to start with the training data where you have both the attributes you're going to use to make these predictions and the predictions themselves that you want to get out, right? And so that's basically what this instance case class is, right? You need to have both your map of values, right? Your map from feature names to values, and you need to have your target distribution. And I still tend to think of these as distributions, and they're still kind of you know, structured as distributions, even though this is kind of a degenerate case of a distribution, right? Because this is like a distribution with exactly 1 element in it. But it might be useful to weight them differently, and so you might end up you know, making use of that. But typically, you end up with something like this, where if for each instance going in, you have, say, a map saying, OK, this one's true, so I've got a map from true to 1, map from false to 1, and so on, right? Hopefully that makes sense. And to create, to first just initialize the root node, all we actually want to do is just sum up all of those distributions and get the overall distribution for the entire data set, right? And that's our prediction for the root. And if we never bothered splitting, then we would just give exactly the same prediction out for everything that came in, right? So in a distributed context, what does that look like? So for each, we've got our instances sort of split over a bunch of nodes. And so on each of those nodes, we're going to take each instance, we're going to extract its distribution, and then we're going to sum all of those distributions locally on the nodes, right? So we get those kind of local subtotals of t. And then we're going to send all of those subtotals to a central node in the reduce step that's then going to sum those up and get us our answer for what the root is, right? Are there any questions, by the way? People should feel free to like heckle or shout questions out midway through or whatever. OK. OK, fine. So that's nice, but all that gives us is this boring root. The exciting part, the interesting part, at least the exciting part to me, is then the question of what do you do when you want to split, right? So you have all of these possible ways you could split. You have all of these features you might choose to split on. You have all of these values of the features or ranges of values or whatever that you might choose. And you have to pick one. And decision tree learning algorithms are greedy algorithms, right? They're always looking for every time they're splitting a leaf, they're looking for the best possible split at that point, right? They're not looking ahead. But what I want to do is I have this kind of huge space of possible splits, and I need to pick one. So this is showing a few splits from a couple of different features, from color and height. Let's restrict this just a little bit and talk about just let's imagine that we only have one feature that we care about, and we want to know what's the best value to split on for that one feature, right? OK, so we have this table from this kind of slice of our training data, which has this value. And again, we have this distribution, and we want to know what to do. What we need to do to decide on how to split this feature is we need to build up not just the distribution of outcomes, of say trues and falses, but the joint distribution between the possible values for this feature and the possible outcomes, right? And here we're going to do just this naive thing again of having maps of maps, right? We have a map of values, and then that's pointing to these maps that represent the outcomes, right? And we'll call that type that joint distribution type S. And again, this is a generic type, right? This joint, we don't care at a framework level. We don't care what the distribution type T is, as long as it's something we can sum. And again, we don't care what the distribution type S is, as long as it's something we can sum. So I'm showing it with this sort of somewhat naive exact joint distribution of a map of counts, right? But this is where like count min sketch that Ian talked about, for example, fits in really nicely, right? So if you have a huge key space, rather than having an exact joint distribution, you can use count min sketch to give you an approximate distribution of a discrete feature, right? Or you can use some other approximation to get a distribution of a continuous feature, let's say, right? OK, so what does this look like? So we're going to do almost the same thing on the individual nodes that we did to get the root node, right? Which is we're going to sum up these joint distributions instead of summing up just the distribution, right? So for any given value, for any given feature, I should say, we're going to produce a joint distribution from the instance, and then we're going to sum those up locally on each node, and then we're going to send those in the reduce step to another node, and that's going to give us the total joint distribution for that feature, right? And then we need to have some way of producing a whole bunch of possible ways of splitting that feature from that joint distribution. And so there's a splitter trait. And again, this is one of these nice abstract traits that like someone else can implement, right? And what a splitter trait needs to be able to do, it has this internal type S, which is the type of the joint distribution that it knows how to work with. it needs to be able to create one of those joint distributions given a value and a target, right? This actually looks a lot like the aggregator thing Oscar was talking about. It needs to have a semigroup, so it needs to be able to combine these. And then it needs to be able to split them, right? So given a joint distribution, it needs to be able to produce a whole bunch of possible splits for us to consider. And those splits need to be both a predicate, right? So they need to be a way of splitting, and the distributions for each leaf each new leaf that this split is producing. So there's this split trait down at the bottom, which is just some number of edges, usually 2, but it doesn't have to be 2, some number of edges where you have a predicate for which item, which instances filter into that, and then you need to be able to pull out at least an approximation of the distribution that will yield. And so, you might have, for example, a binary splitter here that works, as long as you have a monoid on T. We can have a map from a value to T as the joint distribution type and so on. And that works as long as you have a relatively small number of possible values, right? And then you might do other things for other cases. OK, so what that does then, what that splitter trait does, is takes the joint distribution and then expands it out into a whole bunch of splits, right? Now you have this problem of I need to pick the best split. And so how do you do that? And so you bring in another trait, which is this error trait, which actually gets used in a bunch of places, but this is the first place that it gets used. And so that, again, needs to be able to sort of have this pattern of needs to be able to produce this type, the error type. Doesn't care what the error type is, but it needs to be able to produce it, and needs to be able to combine them. And the idea here is we have these leaves, and we have these leaves that have these individual distributions in them, and we now need to be able to produce the error at each of those leaves. And the error trait is set up so that it takes an actual distribution and takes a predicted distribution and comes out with the error. And in this case, when we're using it, the actual and the predicted is the same, right? We only have the training set. We're only evaluating based on the data that we have right now. And so the question really we're asking is, if you were making a prediction from this distribution that you've got locally, how good would that prediction be? And so that ends up looking really often like you're computing the variance or something, right? Because your prediction might be the mean, and then your error is going to be the squared error on everything that you use to produce that mean, and so you end up with the variance, right? So Breyer score error is kind of like a variance for binary classifiers and multi-class classifiers, and it's one of the implementations in there, right? And so your error term there ends up being this mean squared error, which is just an average. OK, so now you have a split, right? Now you can expand this tree, except that we only looked at one feature, and we need to look at all of the features. And the nice thing is this can start happening sort of more and more in parallel. So actually, we're not just outputting one joint distribution at all of these nodes for each of these instances. We're outputting a joint distribution for each feature. And so in parallel, each of those can also be producing these joint distributions and producing these subtotals of the joint distributions. And then those subtotals of those joint distributions can be sent off to some different node in the reduced step, which can then be looking at that joint distribution and producing all these candidate splits. And those candidate splits can all be evaluated, and the best one on that node can be picked. And then we can bring all of the sort of best candidate splits together in one place and pick the very best one overall, and then that becomes our split. Except there's a whole bunch of different leaves of the tree. There's a question? Yeah.
Do you constrain it to be attached, or sorry, like on a particular feature? Can you sort of look at splits that combine like subsets of features?
The question is, do you allow a split to be across multiple features And the answer is no. Each individual split has to be on a particular feature, and you get multi-feature interactions by like different levels in the tree, right? So you have a split on one feature, and then on the next level you'd have a split on the other feature. If you wanted to do something with a combination of the feature, you would create another feature that was like yeah, exactly, that just combined, was the cross product of those two, right? So yeah, so this is happening in parallel for all features, but then of course this is also happening in parallel for every leaf of a tree. And so each leaf of a tree we are individually considering, and so you can, but it's all still one pass through the data, right? Because you can feed in the training data, and the first thing that you do with the training data is figure out which leaf of the current tree you've got that training data would go to, that instance would go to, and then all of its information about the joint distributions gets associated with that leaf and summed independently with the other instances that are in that leaf, right? And so that's all happening in parallel. But actually, you're not usually building just one tree, right? So usually you're doing some kind of ensemble method, like a random forest, where you're building a very large number of trees. And so you have this another step of parallelism where all of this is happening for every feature, for every leaf, for every tree. And so you get a huge number of these things all being summed up, right? And so how does that work? So you have this other trait that comes in, which is a sampler. And the sampler's job is to tell you for each instance that comes in, for each tree that you are producing, whether or not that instance should be considered when training that tree, or in fact, how many times it should be considered. Because for a random forest, for example, you do this bootstrap sampling thing where you actually might use a given instance 0 to n times in a given tree, right? And it's also the sampler's job to tell you whether an instance maybe doesn't appear in the training set at all and should be used later for validation, right? Because you want to train this stuff on one set of data and then you later want to evaluate it on a different set of data. And so that's the sampler trait. So you have a sampler trait for just build a single tree with everything. You have a sampler trait for let's do k-fold cross-validation, which will mean something to some people and won't for others, and that's fine. You have a sampler trait for random forest and so on. And I showed the full instance case class there. I don't know, it's a little bit small type, maybe people can't see, but the instance case class actually has a couple of extra things that I haven't talked about yet. One is a unique ID, and this is important just to be able to have a seed for the sampler, right? You want to be able to consistently assign these things to different trees and so on. And the other is a timestamp, just because this comes up so often that you want to do some kind of out-of-time validation, for example, right? Everything before a certain time gets used for training, everything after a certain time gets used for validation. And so it's useful enough, it's just good to have it in there. To Oscar's point about composing, these things compose, right? So a lot of these things compose, but samplers compose, which is maybe not obvious. So for example, you can have an out-of-time sampler that wraps around a random forest sampler in the other sampler and changes, doesn't change most of the methods, but changes this question of whether something goes into the training set or the validation set, right? So you can take any sampler you have and wrap an out-of-time sampler around it, and that'll work, and so on, right? OK, so a slightly more complete picture of what this looks like in Scalding is this, where actually when you're constructing the trainer, you need the training data, and you also need to give it the sampler, which is critical for sort of everything you're doing. And then implicitly, it will start filling in the other stuff based on the types of your instances, right? So it'll implicitly find a splitter for you. It will implicitly find an error function for you. And you can override these, of course, but there are defaults in there. So normally, you don't need to think about this stuff too much, but it is in there. I don't remember why that slide's in there. And so one thing I've been glossing over through all of this is I've been pretending that there's this one type V, which is these feature values, right? But in reality, you don't normally have a single type for all of your feature values. You've got some kind of heterogeneous thing, right? Sometimes it's like all doubles, but it's not usual. And so how does that work? And so the framework is in some sense kind of agnostic about that, but in another sense, it has a way that is easy to do, which is that it provides this trait dispatched, which is kind of like an either or something in Scala, but has 4 cases instead of just 1. And so the idea here is you can have 4 types, and it's kind of a union type, right? So each instance, each value in your map is going to be one of these 4 types. And the idea is that you have an ordinal type, which is to say, some kind of like int, right? Something that is ordered but has a discrete number of values. You have a nominal type like string, which again is not ordered but has a sort of small discrete number of values. And so for those, you're going to use splitters that do these exact representations. And then you might have a continuous type like a double, which is ordered but has an infinite number of values, or a sparse type, which is not ordered but has an infinite number of values. And so that's useful for like IP address or something, right? When you have these features that just have an incredible number of different values. And usually for continuous and sparse, you're going to use splitters that use these approximate data types, right? That use count, min, sketch, or something like that. So the idea is that you can set this up so that you pick, or have the framework pick for you, 4 different strategies for each of these, and it'll recognize the value coming in, the type of the value coming in, and pick the right one to use, right? And so then actually your feature maps look kind of like this, where you have the feature name, and then it goes not directly to 3 or blue, but to these wrapper types of whether this is ordinal or nominal or whatever. And that's just for fun. Like this is a dispatch splitter, which just wraps around 4 other splitters and does the dispatch. And the code gets kind of crazy, but it's written for you, so you don't need to deal with it. So the last thing that I wanted to talk about before getting to questions was I mentioned that that one error trait gets used for a bunch of other stuff. And it's worth talking about what other stuff the error trait gets used for. So trainer has a bunch of other methods. One is validate, where you just want to know the error of your model. And so there, it's using the sampler not to pick out the training set, but to pick out the validation set. And there, the fact that error has a semigroup associated with it is critical, because what's going to happen is it's going to take each item, in this distributed model, it's going to take each item of your validation set and compute the error, right? So it's going to throw your model at it, find the prediction, get the predicted t back, then ask the error for the error object given the actual value that you have on the instance and the predicted distribution you got back. And then it's just going to sum up the errors for all of your validation set, right? So that's why it needs to be a semigroup, because you, again, want to be able to sum these up in a distributed way. Feature importance is kind of cool. So the question is, which of these features that I fit in is actually useful? And so what it's doing is going, I'm not going to go through the full algorithm, but basically walks through your validation data and just permutes it a little bit. So it'll take some feature value and change it, and see what the error is for each. It sort of groups the error by which feature was permuted, right? And so then you can rank the features by how much permuting that feature affected the error. And so this, you can see, has an ordering type class on feature importance, right? And pruning, which there isn't code in there right now for, but there has been and will be again. You can take an individual tree, and again, with this same error trait, you can look at what is the error individually on 2 leaves. Or if I combine the distributions of those 2 leaves and get a parent distribution, then I can look at what is the error for that parent distribution. And if that's less, then the leaves are useless and I should get rid of them, right? And so then this is less important if you've got like a random forest, more important if you're working with a single tree that you want to be able to prune that, right? So, so this error function becomes extremely useful, and as people who've probably done a bunch of machine learning know, it's like very nice to be able to define your own very customized error function for whatever the particular problem you're doing is, right? So, I expect, like in practice, almost everyone who is using this is going to implement their own error trait, and so it's nice that that custom error trait you've got can then be sort of fed through all these different parts of the system, right? OK, just some links and questions. Planet was a paper out of Google that inspired the design of this pretty heavily. where they talk about how Google does decision tree learning on top of MapReduce. Scalding and Algebird obviously provide the foundation for this, and Brushfire is the framework itself. Questions?
Just like in your experience, like how long does it take to train like a non-trivial like random forest?
Yeah, so you know, it's not fast, right? So the models we're training at Stripe, which are, you know, tend to be a few 100 million instances, but like pretty big, like a large number of features on each of those, on a relatively small Hadoop cluster, and we end up seeing like a few minutes for each level of the tree, right? And so if you want to train something like 20 deep or something like this, then it ends up being a few hours. If you're doing something, you know, really complicated, if you're using like a lot of really sparse features or a lot of like continuous features, that slows it down more, and so because the proximate algorithms take more time. So yeah, I mean, certainly order hours, not order seconds, right? It would be very interesting, by the way, to see if Spark could improve that considerably, right? It's quite possible. Also, like, I haven't done a ton of work optimizing this, right? So.
Thanks for the great talk. Is this the first time when Brushfire is actually publicly available on GitHub? So is it fair to say this is open sourcing Brushfire at the Scala meetup?
Brushfire was open source about a month ago or so. So this may be the first public talk that acknowledges that it's open source. Yes.
Thanks.
Speaking of Spark, I've noticed after the NE Scala or PNW Scala conference that there's some interaction between you and Eric Osheim about potentially getting a version of Brushfire working on Spark. Do you know where that stands, or if that's something that's...
I don't believe anyone has done much work on this. Eric was looking at it. Vitaly Gordon was also looking at it. I don't think either of them have done much more than kind of poke at it. I should say, like, the dependency on Algebird is very heavy here. The dependency on Scalding is very light. It would be very easy for someone, I mean, it would not be a ton of work for someone to port this to Spark or whatever else, Akka or something, right? And I would encourage and love and be happy to help with that. Scalding's just what it was convenient for me to build this on, but I did consciously try to make it, you know, make sure the abstractions as much as possible were not tied to Scalding. Awesome as Scalding is, of course. Cool. Well, I'll be around for a few minutes if people. Yeah.
Thanks, Avi.